screen, this white screen, right, where I put down some basics together. Perfect. And I'm going to, with your permission, close the video. Okay. So now we are focusing on the fundamentals. Sorry. And for those of you who are already very, very familiar, and you may feel a little, bored and dragged, don't worry about it. We'll make sure that there is something even there, something interesting even for those who already know the subject well. The way we approach this subject is a little different because it's very practical, and we are always in the middle of actually putting together solutions for people. So with that context in mind, we will have to understand the subject in a very different way so that you can also teach the same to your students. And I'm aware that you guys are all esteemed professors and assistant professors who's taken up the challenge of teaching machine learning and AI, the most cutting edge technology out there today, to the next layer of minds which are going to come out in a few years. And it's my privilege to be here. I thank Dr. Manjunath sir really for his vision, and Dr. Manjunath HOD AIML for his vision and how he thought through this and said, this event is very important for all of us to get this insight. So with that, let me start off the main session, which is okay. So here we go. The question is, how can machines actually think? So machine is only capable of digital calculations. So how do we get any analysis or computation related to the world done? So for that, we have to go back in time, and we have to study this, that the real world problem which Alan Turing and von Neumann were trying to solve was they wanted to these Alan Turing and von Neumann both were mathematicians, and they wanted to build a machine where a mathematical algorithm can prove theorems. Okay, so they didn't want people to work and get the load of proving a theorem, proving anything, like prove Pythagoras theorem, something like that. So they're envisioning whether machine can solve something. So for that, they wanted to build a computer in 1940s. And the first attempt of building the computer itself was to understand the brain itself. So they were actually doing research on brain. Okay, so when they saw the research on brain, and then they realized, acha, they can actually create an artificial neuron. This thing what you're seeing here, okay, this thing what you're seeing here is a mathematical concept that they created. But they learned in 1940 or 1945 when they created this artificial neuron, there was no technology to implement this. Okay, so this was envisioned by these great pioneers so much, much earlier. And then of course, then we waited for a long time for the computer to be invented, and then all the data structures that are there in the computer to get structured. Correct. So let's see that. So when we talk about the data structure, the mind, and what is the comparison between a computer and a mind? So if you see, the mind or a brain is capable of only three things, according to me. Our minds, if you think about it, we are able to only do these things: count, feel, and decide. We can feel, that is the innate nature. Feel fear, feel happiness, feel joy, feel. It's all chemical, right? So we can feel. Then we developed a system to organize our feeling in terms of intensity. How much feeling do you have? How much joy? And how much sadness? We wanted that because it was natural. When the brain is feeling the same thing, it's always joyful, there are 100 different things that are giving you joy. It is natural for us to put a number to how much joy, right? So counting as a system was obviously there for us to discover it. And our mind gives you this count because our mind has an innate circuitry which keeps track of time, and this time and the memory of time, okay, this is what makes us intelligent. And they discovered this, and then they said, what can we do to create an artificial time stamping and artificial memory keeping so that we can count the kind of feel that we have, using which we can take decisions. This was the loop. So you see, based on feel and count, we decide. You think about it. Even now, you're trying to feel something. You're trying to connect with me, or maybe some people are not connecting with the idea. And okay, let me now put a poll out there. Can you all give the say a thumbs up if you are able to understand my approach? If not, can you give me a thumbs down uh, if you want me to change, or if I'm getting ahead of my own this one. Perfect. I thank you so much, everybody who's contributing with their thumbs up. I really thank them, because that gives me the sense that we are all connected. Otherwise, this system won't allow. And of course, we cannot have everybody turn on their mic. It will disturb the whole recording, because this whole thing will be recorded and it will again be given to you. So that way. So now, can we? The question is, see, based on the feel and count, we decide. But can we make a machine feel and count, and then build a? See, this is the statement I want you guys to see. Can we make the machine feel and count, and then build a logical network which uses the feeling and counting to decide, right? And this one gets directly mapped to the von Neumann architecture. Okay, so that was what they did: build a hardware for computing, and then you have input, mouse, voice, keyboard, numbers, and text, memory to store, processor to build logic and automate, output to see output. That's it. This is the whole thing. You see, this is what it is: the input system, the memory to store, the processor to build logic and automate, and this is where all the programming goes in. This is where all the programs get stored. And if you think about it, everything you see is in numbers and text. I would say numbers and text, including I want to again bifurcate this text as symbols, which are nothing but characters. Something like, if I key in the number 3 into a system, it can be a character also, it can be a number also. It depends, because the moment we cast it as a number, then it becomes a number. So I'll slowly make you understand the importance of seeing things as a symbol or a number. We're going to get there, okay? We're going to get there. But I have something, because I'm from Analogica, and for a long time I worked in the industry, and now also we consult with a lot of the defense agencies on AI, because we are called in whenever there is a AI problem, and they want to know from us what aspect of their problem can be solved using AI. Not everything can be solved. Sometimes AI is just too much of a pain, where if else is okay, why do you want something else? When if else works, let if else work, right? You understand what I'm saying? If else is something which is very common in programming, but you cannot have if else statement for all possible conditions. So if you want to migrate or move on from if else to what else, if your algorithm can think what else, then your algorithm is learning, right? But then that's what we're called in for. And the other effect of being in this industry is that we started Certishort so that we can train people and give experts to the industry on machine learning and AI. And we have been successful at it. I'm not saying we have placed thousands of people, but definitely the numbers that we have placed are in 300s to 350s. Okay, and that it makes us happy that we've been able to contribute and take and identify good people with great mathematical intuition and turn their energy into good data scientists in AI. But to do that, that's the thing that I have in front of you now. This is the approach that we take. Whatever you're seeing right now, this is how we think. Okay, so let me now, yeah, I'll start from here. The problem of counting. Back in the time, we call this the story of X. Okay, story of X being a variable. So how does this variable concept come into our mind? If we start from here, everything starts making sense. So take it easy, get into the flow of this small story that I'm going to be putting out to now, and we'll understand. Let's look at this picture first. Let me grab a thicker pen and then get your attention. Look at this picture. People are just, just living. There's no career. There's no insurance. There is nothing, right? There is no economy, nothing. It's just people living and getting through the work, getting through the day, staying alive at the end of the day, and getting up morning in the morning. That's their issue. Food and sleep and staying alive, right? When a life like this exists, do you need a very complex mathematical system? No. That's why you had Roman numbers. Roman numbers hardly after 20, I think it becomes messy, but you don't have much to calculate anyways. But then what happens is our brain, our human brain, is a very complex brain. It keeps on getting better and better with practice, right? So that brain is eventually becomes a beautiful engine where we reverse the chaos. Means we're constantly going towards organization. You can see the world is also experiencing the same thing, from industrial revolution to space revolution and then the AI revolution. What have we done? We have organized and automated everything. And still, I believe only 8 to 10% of our life's problems have been automated. The rest of the 90% is yet to be solved, and AI is a beautiful promise for that, right? But to be able to do that, we need to create great engineers. And to be able to create great engineers, we have to be able to motivate them and make them love the subject, make them connect with the subject. And that's the whole attempt here. Anyways, moving on. When life becomes a little like this, where this particular person now gets the confidence, then he can handle more. And this person gets the confidence, then he can handle a lot of stuff. That is when a more complicated system is required. So every time you see mathematical systems with more symbols, more complex equations, don't be bogged down by it, because it is there to make your a complex system much more simple, right? So modern world complexity is huge. We need to reduce the modeling capability to bare minimum and still represent all the complexity of the system. This is the takeaway. See what is written here? Modern world is complex, right? You agree? We need to reduce the modeling capability. Means make it so simple, so bare minimum, yet be able to represent all the complexity of the system. That's why you see complex math. So once you start understanding these symbols, everything is cool. In fact, let me just draw some this one. I'll just show. Wait, let me go and see the poll result. So poll result says 58% of people want basics to be covered. Out of 58 people who voted, 34 wants basics to be covered, and 22 say they're intermediate, and about 2 people have said they are a pro. That is fine. But you see, if you know that there is something called a Gaussian distribution, which is called a normal distribution. It's called normal because most of the life events are distributed under this. So this says that about 66% of the people will fall in the first sigma. Then about 13% will fall in the second sigma. Then you have third sigma, right? So given any event, 66% of the people will fall between the zero and the mean and the first standard deviation. This is statistical concept extensively used in machine learning. Even in one of the concepts here in the ML lab, you will be using this. Okay. So you see what has happened here in the real event. In the real event itself, I can see that not 55, but uh, this is a standard normal distribution. But our distribution, what we can see is a little like normal distribution, where 55% of them are here and rest of them are skewed extreme, and then a few of them are here, right? So these, see this, what is this? This is a probability density function. This shows the density of the probability. It's a function which defines how dense is the probability. Okay, I'm not going to skip. I'm just telling you how relevant all these things are in real life. Everywhere you see things are happening. We just have to have the eye to communicate and calculate these things. Okay, so our sessions are going to look like this. We're going to have a break at 10:30, and then after 15 minutes, again, we'll rejoin. So our sessions every day will be, the first session will be for 90 minutes. The second session will be for 75 minutes. The last session will be for 60 minutes. Okay. Of course, today we got delayed, but don't worry about it. Whatever is not covered, I will eventually cover it. You don't have to worry about it. We'll take time. I'll send you videos if possible, but I'm going to make sure that all the exercises are covered. And exercises are very simple once you understand the basics. Now let's get back. Then what happened, once the systems are created, you have all the numbers, correct? You create a number system for our own ease. And in that number system, some mathematicians is going to find some kind of pattern, and they realize that, hey, there are a lot of numbers which cannot be divided by any number, so it becomes a prime. Then there's a lot of numbers which can be divided by any other number. It's a composite number. Fine, it makes sense. So what we are building here is we are building abstraction. With time, what we are building, we are increasing these abstractions. Abstraction means what? Abstraction is the concept where whatever is your thought, okay, you are putting a symbol to it. So something which never ends, you put a symbol like infinity. And then something which gets added, you put a symbol like summation. This is abstraction. Okay, if somebody wants just a little clarity of what I'm saying. So as we keep on thinking better and better and deeper, our abstractions increases, right? So what happened next is, okay, there was all these numbers there, and then suddenly somebody said, hey, can we create something called a number series? Can you create a small algebraic setup where you can sort of, if you know the pattern, so you can predict the next number. So something that like that we have seen in our life. N is equal to an plus n minus 1 into d is an expression which will give you the nth term. If you know the first term and how many terms, which term you want to predict, and what is the common difference. If you get that, then you can predict that number. Why? Because you know the common difference, right? So you see, already we know, algebraically, we know we are able to predict a certain thing. So I'll get back to this. Hold on to this thought. I'll get back to this. This prediction is very, very, very mathematical. It's not magic. It's just trick, mathematical trick. We'll have to understand all the tricks. But I think the most beautiful thing happened when they said, let the number be x. Okay, so I'm going to zoom in here, and you see we started with numbers. Okay, number series, and the first question was, let the number be x. And why I'm saying x here, because this is a story of x, right? Everywhere you're seeing x, that variable, what you're going to do with these variables. That's what the whole story is about in machine learning. Can you make a machine learning algorithm understand the variations that your variable will undergo? You see what I'm saying? Can you make your ML algorithm understand the variations that a variable experiences? You model this variation, you model the machine. Where are these variations coming from? Variations are coming when you decide to collect data. You decide to collect data of health. All these tables that you have is health variation. Each one has its own blood report or heart rate or anything, any variable, right? How is that changing? If you model it mathematically, then you are very, very close to building the model. So that is the context. That is the key takeaway. Okay. So for that, we have to understand and appreciate these systems. So let the number be x, created algebra, and using algebra, we're able to, at least put a system on paper, in a sheet. We can bring that real world. We can bring the real world relationship to a sheet of paper. Using what? Using symbols that we call as abstractions, which is going to hold a thought that is interesting to you. Infinity, summation, pi, or the thetas, the slopes, all of this. That's a real world abstraction that has to get formalized into a system using symbols, right? So I hope, can I see a thumbs up if you're able to understand this? I see a raised hand. I see a raised hand by 30 minutes ago, 20, okay, 30 minutes ago, fine. It's making sense, everyone? Is it? Okay, perfect. Thanks, thanks, thanks. All right, so, and it's like, um, there's a quote by Abraham Lincoln which said, if you want to cut down a tree, if you want to cut down a tree, you spend at least, if you have 2 hours to cut down a tree, spend at least 1 hour sharpening your eggs, right? So that's what we are doing now. We are sharpening our brain because the first day we want to all connect with the idea. Okay. Now see, the first question was, let the number be x. What is the next question? How much of x? This is a general mathematical flow. Nobody in this world can question this flow. The first thing is invention of numbers. Next, in place of a number, you put the variable. That is when I say, let the number be x. Once the x is put, then we want to see the variation of the x, and that is given by calculus. Okay, so it's very important that you see if their calculus is like combining geometry, algebra, and variations. For example, geometry, you see these figures here. If you want to calculate the area of any of these figures, there is formula is ready. Length into breadth, half into length into breadth, pi into radius squared. And this is ready. But what if you want to calculate the area of this curve here, right? You see, you able to see this curve here. What if you want to calculate this? Where is the length and where is the breadth and where is the stuff? But this can be calculated only when you bring this entire thing, you see, you bring this entire thing into this frame. This frame, that frame is called the reference frame. Okay. So the most important thing of machine learning, algorithm, or ML, deep learning, anything, is the reference frame. In fact, everything is measured only with the reference frame. And reference frames are many, but usually we use the Cartesian coordinate system. So this is a Cartesian coordinate system where one is x, one is y, you can have one as z. These are all variables, and then the whole drama and the story between x and y and z, the combinations of it is what makes sense. Finally, what happens? If you want to know the area encapsulated by this curve, this problem is called the area under the curve. Okay. And who gave this area calculus for the first time? That was Newton. And what Newton did has changed the history of the world because Newton calculated the area under the curve. You know what it means? It means that when two ships are fighting in a naval battle, now I'm going to take you to the history. When two ships are fighting in a sea, and one is a British ship with its British sign, one is a British ship, and then because these people have optimized the area under the curve, they know exactly how much energy and what angle to give to their cannons so that they can destroy the enemy ship before the enemy ship can destroy them. That is the reason why the English Navy was undefeated. And that is why everywhere the East India Company or the British Empire, right? They say the sun never sets on the British Empire because they're spread everywhere. Why? Because the Navy is so strong. Why Navy is strong? Because they optimize the area under the curve. So you see how important it is. And now what has happened in machine learning is we are not interested in the curve. Of course, we are interested. I belong to the defense solutions. This one, so this curve is still very important. But now this has to be calculated in real time and not pre-calculated. It has to change. The drones are coming into the picture now. Drones are AI based, and there is no one trajectory. They'll just go here, 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 and everywhere, and then their goal is to attack. Okay, now that the whole system is different. But what are we using this for now? This area under the curve, this curve for us today is the relationship between x and y. If x is, let's say, age, and y is, let's say, salary. So the relationship between x and y is now a curve for us. And for us to solve the area under the curve gives us the ability to Just bring all this data into an algebraic equation. That algebraic equation is nothing but your machine learning module. Always. Okay, always. That's the whole thing. That's the whole thing. Once you understand and appreciate that, yes, this is what is at the core and there is nothing else, then you'll feel confident that, in which direction you should put your energy into so that you can start learning, right? Anyway, we'll understand. So this was a 2D plot. And the moment you have a three-dimensional, let's say this is age, right? This is age, this is salary, this is experience. Third dimension got added. We can add, right? We can collect the data. We can collect people's age, we can collect people's salary, and then we can collect people's experience. And then we can say, I will use experience and age to predict the salary. Or you can say, I will use people's experience and salary to predict age. It's up to you. But you see, the point on this, the solution for a particular variable here is on a 3 or 2D mesh inside a three-dimensional space. Okay? So what if you have a fourth dimension? What if you have a fourth dimension? What if you have a fifth dimension? What if you have a sixth dimension? We have, because we are in machine learning and in deep learning, we're solving the variable lengths of 10,000 variables at once. That's the level at which the computer is able to solve. How? So that linear algebra, that algebra that we sought now, has now become linear algebra. Okay? What is so linear about that algebra? Why is the algebra different and why is linear algebra different? Because in algebra, you're just about plotting the simple relationships. But in linear algebra, we express this relationship as linear combination. So the moment linear algebra comes up, the vectors come up. Okay? And the matrix forms come up. So I'm giving you a slight hint as to what this drift is all about. So that you can ask ChatGPT, you can use ChatGPT to give you an intuitive feel for the difference between algebra and linear algebra. It's very important. If you are into this field where you are you are beginning a career, or you are beginning your PhD somewhere, and all this information, the thinking is very, very important. That is, I assure you, it has to be that way. Now, where is x? See, let the number be x. How much of x? Where is x? Is a coordinate system. Next thing is, the next question is there an x? Give me a thumbs up if you appreciate the flow of the questions that we are asking about x. Only one? Everyone? Okay. So I hope you guys are connecting with this. And if you are going to ever give a lecture to your students, I'm going to give you this PPT. Please follow this, and you'll see how easily everybody will connect with this, right? So now we're asking x. How much of x? Is there an x? Is where the next. This is where the probability comes up. So all the time, all the variables that we think that x will hold, we can ask a certain question. First, we said, let the number be x. Then how much of x? Then where is x? That is the coordinate system. Is there an x? That is probability. Will it happen? So we'll learn about it, because we have one experiment here. Let me just open that up. We have one experiment. I don't want to just go into this one completely. So I just want to make sure that we are all understanding that our whole attempt here is actually to build that space for you. So I'm going to just bring this here. Am I audible properly, or am I too low? Is my voice too low? No? Okay. Okay. Huh? Acha, people are sending WhatsApp messages. I think, how do I increase the volume? I don't have, because I'm connected to my. Has it improved a little now? I've improved the system voice. Let me see. Okay, Clearly, you're audible, clearly visible and audible. Thank you. Thank you so much. Thank you for your. I'm really sorry if someone else is experiencing, low volume. Please, just do some adjustments with your speaker. Put me uh, on Bluetooth speaker if you want, or do the needful, please, because I'm in the middle, so I'm not able to help you and correct it on the go. But here's the thing: the screen. If you see the screen, you see there are all these algorithms that are there, and one of the algorithm which is interesting here is your knife-based classifier. Okay, this is where the probability comes up, and you see this creating histograms and numerical features and all this. This is where statistics come in. Okay, and all this creating correlation matrix and heat maps and all that. This is where your data visualization and your effective utilization of pandas and everything comes up. And this principal component analysis, reducing the dimensionality of a particular data. That is what this is all about. I just told you linear algebra, right? If there are 10 dimensions, how do you reduce that? That linear algebra perspective is there. So this lab is not simple. Okay, they have planned it very well. And of course, this algorithm was very new to me, so we enjoyed learning this. uh, yeah, but there are other better algorithms to solve the same problem. But it's interesting. This algorithm is important. I can appreciate why VTU would like to put this algorithm. It's really something which is. So we are not going to rush into it. We have our time today. We're going to just do three algorithms, the first three, and then we have this. Today we'll do this linear regression, polynomial regression using Boston housing dataset. All datasets are there with us. You don't have to worry. Everything is there with us. I'll share it with you. All of you will open it up on your system. I hope everyone's got the Jupyter Notebook or VS Code or something running. And it's very simple. You guys will know how to do it, right? And then there's decision tree. Everything will understand knife-based classifier, then k-means clustering. Overall, everything is simple, not much complex, easily done. But thing is, it is easy only when you understand the context. Otherwise, it looks like a very complex endeavor, right? And then how do you make your students understand it? And eventually, what are you going to ask your students to by heart these codes? Is it possible? I have also studied, right? So I also, there was a point when I found myself by hearting a bubble sort program. Okay, bubble sort, the heap sort, the data structures algorithms that we all studied. And back in the time it was easy. We could find the logic. But here in Python, it is not easy to by heart because there is too much to memorize. Everything is API, everything is some library. How will you by heart so much library? So you have to change the way in which you're going to assess your students. So for that, we need all this information properly structured in your mind. Okay, is there an X is very important question, but the most beautiful thing that statistics gives you is, it says, let there be many X. And the statistic says, I'm going to give you the way in which you are going to measure the things that are happening inside of data. So when you have, let's say, this table in front of you now, you have all this table, and you can see in the left side there is country, then there is salesperson, there's order ID, units, order amount. You see, think of this as, look at this like a computer scientist, then look at this like a data scientist. A data scientist will wear the specs or the layer of stats. Then we have to find the commonality between this data scientist view and the computer scientist view. What is that? See the data. I'm going to write it here. Data. What is country is a variable. And what is here? Just some symbols, right? USA, UK, USA, UK. Just some symbols. Okay. This is just a nominal data. Okay. So it comes under quality. And what do you have here? Units, numbers. This comes under quantity. Qualitative analysis, quantitative analysis. This is just a quality. But what happens in our data science problem is that when the data set is given, it is a combination of quality and quantity. And quality, quantity together, we have to crunch it inside our algorithm to get a prediction, right? So, but we should be aware. If you take the computer science, let's say data structures perspective, one is your all your numbers, your integers, and all others are your symbols, right? For integers, you have all this int and float, and for symbols, you have characters, strings, same thing. Quality, okay. The quality thing comes to symbols, the quantity thing comes to the integers. It's the same thing. So data structures, why data structures and algorithms, why data structures are important is because unless you understand the data structure, you will not know how to approach it. And the same thing is true for machine learning and data science. Unless you understand what kind of data you're dealing with, you'll not get the first direction to move forward. It's like you get into a car, and if you don't know where you're going, you don't know what you're doing. Correct? You know where you're going, and you know what time you're going. You know how much time it's going to take, how much fast you should drive, and all these things. Right? That's how this thing pans out. And you see there is qualitative data, qualitative data only nomination, qualitative data only nomination. Then this is another timestamp data, although it's a number, but it is just a different kind of nomination where it can be reordered, right? And there is order ID, then there is units that this person sold, then the amount. So you see this, if you want to apply some regression and you want to say, I want to build a model which can tell me whether US people are selling higher or whether UK people are selling higher. I will just use these two variables. This is the question. Can I build a model where my input is the order amount and my output should be which country it is going to be from? If I put 2,500, the system should say most likely it is a USA person. Can you build a system like this? It's a question. I'm not building it now, but these are the questions. And yes, you have to take this order amount and country and you have to bring it to what we call as the reference system. Then you decide in the reference system where is going to be the X, which one is the Y. Because now you are building the model in such a way that the order the order amount, okay, you're predicting UK, right? So the country depends on the order amount. That's what you're doing, right? So usually your equation is Y is equal to something. So here, this is the country, UK or USA. You just have to, either there is UK or USA. Then you have all this order amount. Now you see the problem. USA and UK are nominal numbers, but this Y is starting from zero and increasing. Can you really bring US and UK here? Is it even possible? How did you bring UK, US and even what context? Because it won't fit here. It is not something that goes on a number line at all. Now you have to transform this data. That is when your feature transformation comes up. Otherwise, simply just putting people here, let's say you Fuller, Gloucester, Bromley, Fingley, you want to put them here. On what basis are you going to put Fuller near to the zero? And on what basis are you going to put Callahan away from zero? Are you arranging them in terms of how much they weigh or how tall they are? Where is that extra information? See, these are the questions. When you ask questions like that, on what basis? So for us, it's always like how we always think, and this line of thinking has always helped us. I mean, personally, I'm saying in my being in the industry and why we are always called by some agency, very critical agency, if they trust us, that then we also have to be able to deliver it, right? So how do we know we are thinking right? It's because my question is very simple. I always look at the references, then I look at the data, then I say which of this data can I bring here? Because if I cannot bring it here, can I predict? No. Because if you cannot measure, how can you predict? Because only when you measure, you can build a relationship. Only that relationship can help you predict. Remember this, no measurement. In fact, I would say no reference, no measurement, no measurement, no prediction. This is the mantra. If you want to put this in your lab, print it out and put this for everyone to always remember. Put a reference frame. In fact, if you want, I can send you. I have a PDF of it. You can print that out and put it in your lab so that everyone always remembers that no matter what data you have, do you have the reference system to measure it? And statistics gives us that reference system. Okay. Statistics gives you the concept of numbers, mean, standard deviation, range, skewness, kurtosis, and all this P25, P75, the confidence intervals that you have, the quartiles, the median, the summation, all of this together gets added into a machine learning algorithm, and that's how you predict. And when you start predicting something, okay, when you start, there will be a break at 10:30, don't worry, okay? If anyone wants a break right now, or can we wait till 10:30? All clear? Thumbs up to continue. Perfect. So let me try get this here. Okay. Okay. All right. So now that we have done with that, quickly I'm going to recap. Quickly, I'm going to bring your attention to types of machine learning. Okay. So there is something called semi-supervised and all. That is fine. In the textbook, it looks fine, but fine here. In fact, in the real world, when you're trying to solve problems, we are not looking at labels and what you call that and all that. We don't think like that. Okay. So we just are concerned of the target. What is it that you want to predict? The target. Target usually are only two types. Either you're predicting the target is a number or the target is a symbol. That's it. If your target is a number, then you're regressing. If your target is a symbol, then you're classifying. That's all. Okay. So you have regression models and classification models. Overall, your machine learning has only two kinds of problems. Either you're regressing or you're classifying. That's it. Go and check any algorithm now, 10 years before or 20 years later. You're either regressing or you're classifying. And if this classification is more like a probabilistic prediction, then that also solves and gives you the insight of how ChatGPT is working. Okay. So now this regression and classification together can be seen as a supervised learning. You can supervise a machine learning algorithm to do regression or to do classification. You can have an unsupervised machine learning, but you can't do regression there. You can only classify. Okay. And reinforcement learning, we are not even going to touch it. It's a part of this ChatGPT, how they built this GPT, generative pre-trained model. Okay. This pre-trained model was built using reinforcement learning. It's a very complex thing, but I'll send you, because it's out of scope of this one. So we're not going to spend time on understanding reinforcement learning. Just supervised, unsupervised. You have it. In fact, here you see in the lab exercises that we have, there is something called k-means clustering. Okay. And of course, the VTU says, okay, you have to use the Wisconsin breast cancer data set to visualize and cluster the result. That is fine. Okay, we'll use it. We'll use the data set and we'll do the clustering. But this clustering is what? This clustering is unsupervised, and all others are supervised. Okay, but what is the meaning of supervised and unsupervised? So before we take the break, I'm going to close the difference between supervised and unsupervised. Okay, so let me, how do I tell it? How do I see? Okay, let me open up a data set for you. Okay, let me open up this. Okay, see, this is this one on the left side here. On the left side here, there is a column called diagnosis. M and B stands for malignant and benign. Okay, one is dangerous, one is not dangerous. And for that, the tumor measurements are given here. If the tumor measurement is this, texture is like this, perimeter is like this, blah, 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 all this amazing data that they have collected, thanks to the beautiful sensor technology that we have. Okay, all this data that is collected, they've collected this, and for all this, the tumor was malignant. Same way, somewhere, some other pattern, you see benign. Okay. Now the question here is, we can decide to take up all this data, and we can say, I'm going to use these, whatever I've selected here, this, to predict the diagnosis. Think through with me. My attempt here is, the moment I saw the data, what did I see? I saw the target. Because you see, as a data scientist, when you see, okay, diagnosis is here. Acha, we know which one is malignant, and we know which one is benign, and we know what patterns. So of course, so I'm going to take all of this in x-axis, and I'm going to put this in y-axis, and I'm going to build a model. Now, the moment you have a target, the moment you show the algorithm, hey boss, see, this is the target, and these are my input, the feature vectors, and this is my target vector. If you say this to the algorithm, then what you're doing is you are supervising the learning, because supervised learning means both feature vector and target vector are known. And oh, the drama between the feature and the target vector, whichever way it does, is the model. The model captures that drama. Okay. And the drama is what? Usually the drama is all about the variations. That's why statistics is important. The mean, the median, especially the mean, median, variance, and standard deviation. These four concepts are around which everything plays. Okay. Now, what happens if it is unsupervised learning? Unsupervised learning, what happens is, in this we don't know this. We don't have this data at all. This target only we don't have. What can we do with the remaining data? We can cluster it. We can build a clustering algorithm where we can see if certain variables are all clustering together. And when this clustering happens, for example, you see, so okay, let's just take two, between the radius and the perimeter. Okay, and if you see there are certain clustering happening, means what? For a certain level of radius and a certain level of perimeter, some samples are around here. Then for a high level of radius but low level of perimeter, there is another sample clustering together. Then for a medium level of radius, you see this medium level of radius here, and then for a high level of perimeter, then there are few more. What this means? This means that there are hidden classes which was not obvious to us when we see the data. But when we use k-means clustering, we can see these classes. Now we can say, after doing so unsupervised learning, we have discovered hidden classes. Now those classes now become nominal A, B, C, or in fact your M and B also, malignant and benign. Okay, so this is more of discovery. This is more of, you already know what you're looking for, target and feature, build the model, predict. But in unsupervised, you take the data and you put it in a cluster, and then you create classes, discover if there are any classes inside this. And our ML laboratory here is around, in the next section, when we come back at 10:45, we are going to learn, we're going to start with our first data set. By the time I would have sent you all the things that are important for you. And then from there, you can, clear it. So shall we have a thumbs up? So are you converting the lab programs from AIML brands, since we have different lab programs? We have a question from Pranesh, Dr. Pranesh Kulkarni, and if it is, this is all AIML, this one. But if in case some data science people have also joined that I was not aware of, and if there are some other algorithms that you want us to solve, please contact us and just send us the syllabus that you have, and my team will be more than happy. It will be one day's work for us to put everything together and give you. And if you have any doubts, we'll clear it also. Not a problem. See, we are Analogica, we're certified, we're always connected with university, connected with industry. I'm myself, I'm in the process of getting my PhD. I'm doing a PhD on RAG models, the ChatGPT models. Okay, so I'm building a system where ChatGPT always gives you the right answer and doesn't hallucinate. So it's a hallucination mitigation of general pre-trained models. So I'm interested, and if you have anything, you can always. So that's what I'm going to answer to Dr. Kulkarni, Pranesh Kulkarni, sir. So if you have any other thing, please let me know. So we'll take a break now. Okay, kindly send the recorded video links to practice. Definitely, all recordings will be sent. It's anyway being recorded, not a problem. You can see here, it's being recorded. It's already 1 hour 40 minutes into this, and it's going to be a 5 hours thing. So that's not a problem. It's going to be a big recording, but what we'll do is we'll break it down and send separate. I'll put it on YouTube and we'll send a link to you so that everybody can have access to it. All right, all right, sir. Because I'm also sorry. I'm used to saying guys, people, guys, and all that because our environment is like that. Please don't mind. My hearty respect for all of you is always given. It's a default thing. So enjoy your break. 15 minutes later, we'll come back. No hurry. If you're taking 5 more minutes or 10 more minutes, no problem. I can always accommodate that. Okay. So for now, let's pause the recording and we'll unpause when we come back. Okay. All right then. I'll see you after 15, 20 minutes. Bye-bye.
All right, so okay, so yeah. All right, so we're going to start with the experiment one, which is California dataset histogram box plot. So let's just get the reference in it. First experiment: develop program to create histograms for all numerical features and analyze the distribution for each feature. Generate box plots for all numerical features and define new outlines. Again. Take histograms for all numerical features. Analyze the distribution of each feature. So when you say each feature, that is univariate analysis. Okay, one variable, analysis on one variable. Generate box plots for all numerical features and identify any outliers if required. I would like to take this opportunity here to just give you a brief on statistics itself. I mean, what is the whole idea of stats and what are we going to do when we give something, start doing something? Let me just give you a statistics refresher. It has to be done. No, it's not visible. Stop sharing. It's visible. How many people are experiencing that you're not able to see the screen? Screen not audible, visible? Visible? If it is visible, can you give me a thumbs up, please? Opened up this data set now. Yes, so it is visible. Some of you was experiencing a low bandwidth, probably that is not. Someone saying, Dr. Vanu Swami, like you were saying that it's not visible. Hopefully it is visible now. Yeah. So statistics. Okay. So let's just quickly get into the statistics part of it. Because that's very, very important. I'm going to do statistics with just this window here. Okay, whatever this window. So I'm going to write here and spend too much time, of course, but I want you guys to understand something, want you people to understand something. When you see this data set for the first time, when you observe this data set, see how many things are here? See? 570 data points. This is just the Wisconsin breast cancer data set. Any data set, you see this, all these numbers and then some symbols and all that. Correct? So go back in time and think for the first time when people started collecting data. First time. They just had numbers, that's all, numbers to count. They asked all these questions, X, where is X, and how much of X, and where is there an X, and all that. And finally, they wanted to create a system where, in fact, I will, why not? Why not? Let me pull out my best presentation that I have for somebody who wants to get introduced to statistics. Okay, I want you people to understand statistics in a very different way. Okay, so this news tree, hopefully it's visible. Introduction to statistics and probability for machine learning. It's simple. I'm not going to take much time. I want you to understand one thing. If you ask yourself, what is statistics? Okay. So you would say statistics is all about numbers, calculating mean, calculating variance and all that. But this is what you should remember. Statistics is the discipline of mathematics which helps in determining how false is your guess. This is what it is actually supposed to do. Because this world, because I come from astronomy and space engineering, for me, physics is at the core of everything. And all mathematics and everything, all effort for me was done so that you can understand the world. You can model the world, model the nature, right? So to model the nature, we created algebra, physics, we discovered gravitational constants, we discovered universal constants, the Boltzmann's constant, and acceleration due to gravity, everything. And then we put it in algebra and we started understanding how do I send a trajectory from Earth to Mars. Fire and forget, it will go and start rotating around Mars. All of this is governed by physics. When you start putting data into the perspective, data has so much variation that it will not fall into the standard mathematical models which is governed by physics. There is no physics of the mind. There is no physics of people's interaction. There is no physics involved in how many people are ordering biryani today on Zomato. But Zomato people still want to be able to predict it. So at certain time, what happens is we are all going to start guessing on. Now, statistics brings in a very disciplined approach to tell you that, hey, you go ahead and guess, and I will tell you how false is your guess, because we can never tell how true your guess is. This is not possible. There is no reference system for truth. Okay, there is a reference system for falsity. That something cannot happen. Right? So you take a guess, and I will tell you how wrong you are in taking that guess. Because when you look at the data, and whatever the data is saying with respect to your guess, data will tell boss you are so much wrong. This is the whole drama of statistics. To achieve this state, you need all this. You need all this mean, median, variance, standard deviation, and then your probability density functions. Then, of course, moving forward from there, you have your measures of the moments. So we'll if in case if you want to I'll send you a video for today, where you can watch that and get more insights into it. But moving on from here. Okay. So can we really calculate how true our guess is using maths? Yes. You have to have sufficiently large data, observation, and use statistical methods to do it. Now, where does the data come from? You generated the data. You decided to observe. So you collected the data. So that's where the data comes from. Physicists are also observing the neurons. They are also collecting data. It's the same. Physics, patterns of nature. Statistics, patterns hidden in the data. Okay, I hope this is getting clear. Next. Okay, so what do you call if you are analyzing patterns in physics data? It's called statistical physics. It's there, it's a branch. Okay, now the question is, how can statistics teach machines to learn? Machines can learn to discover relationship between different variables. So you mean to say statistics helps us to discover relationship between data? Yes. So that's all the whole idea is. So now the next question, are all data just numbers? No, they are not, because some are quantitative, some are qualitative. Data that can be measured with numbers, and data, some are discrete, some are continuous. In continuous, some are interval data, some are ratio data. All of it are under quantitative. In qualitative, you're using just words to express it. So there's categorical, there is ordinal. Categorical is just, say, if I ask a poll, how many kind of laptops are you using right now? So you will say Dell or HP or Apple or any other laptop. So all these are just text for me. I can't do anything with it. I can't take the data that you give me and put it on a number line. So it is just categorical. But if you all just take an initiative and say HP so and so, and it cost me this much. And if you say my laptop is so and so, but it cost me this much. If you send me a vector instead of just the scalar, okay, a vector means a quantity and its measurement, then I can take that data to the number line, because now I have a reason, because all the laptops, now I can reorder it in terms of ascending order or descending order of the name and the price. Okay, this number quantity is attached to the nomination now. That is when it becomes ordinal. So always you will see these kind of data: quantitative, qualitative, categorical, ordinal. You want to just take a glimpse of it. You can see now here. Okay, ordinal. There isn't much of ordinal data here, but maybe in some other data set we can find it. We can definitely find it. Other data set. Okay. Am I audible properly, people? I hope. Thank you. All right. So, which is that? It's here. Yeah. Now, types of statistical methods: descriptive, inferential. Okay, you describe the data, you infer from the data. Types of statistical methods: descriptive is how does it look? Inferential, what does it mean if it looks like that? So what are we doing here in the first experiment? We are describing. So this is descriptive statistics. We are just putting everything here in terms of graphs, building some kind of intelligence to talk about, to understand the data. And to do that, we are using certain graphs. Each graph has its own meaning. later remind me that I have a book called Creating Effective Graphs, where each graph, whole book talks about which graph to use when. So I'll be happy to share a lot of material. Those who are really interested and want to book that. So this graph here is a box plot. The other one is a histogram. So we'll learn about this, right? But basically, let's get back to this. So what are we doing? We're going to do descriptive statistics. Why? Because we want to see how the data looks. Once we have done this, once we know how the data looks, for example, you see, once I see this pattern here between, which one is this? Median house value and frequency. Okay, that's a little far stretched. Median income. Okay, median income and frequency. This is a good median income of people and how many times it has occurred. Somebody is earning $1,400 per month, and the okay, this is here, right? Yeah, somebody is earning around $2.5 million a year, and there are 1,400 people in the data set who are earning $2.5 million per year. And there are, let's say, $10 million, somebody who's really rich per year, earning $10 million. Very few people, hardly around 50. So you see this pattern, when you see that, again, now when you see this whole picture is supposed to give you what? It is supposed to give you reason to infer. Infer means what? Infer means you finally think about something. Data set is open. Now, if somebody has, I just got a message that somebody is having, everybody is experiencing that the data set is opening in a notepad. Okay, let me just send you. I think it's here, Boston housing data set. Let me also send you this. Okay. Thank you for bringing that out. Compress to zip file. Okay, because I have this open, it won't allow me. Okay, I'm sending you all the data sets for all the days. Okay, I'm sending you the whole zip itself. Some data sets are inbuilt, some data sets we have to use it externally. Send that. So if you go here, you will see the housing.csv. So let me just open housing.csv for you. All right. So this is one data. Okay. So you see here you have all this data. So let's also check what data we have used. This is housing.csv. Fine. Okay. Same data. See longitude, latitude, housing, median, total rooms, ocean proximity, median. Fine. So this I'm guessing that you guys will be able to open this because all of them are .csv. I think what you did last time, of course, my mistake, that I've sent you this file. Then you must have thought that this California data set is the data set. Okay. This is IPYNB. So IPYNB is IPython notebook format. So when you see this IPython notebook format, this whole thing that is opening up in Jupyter Notebook gets saved as IPYNB file. Okay, this IPYNB is the entire code. And then you have this data set, the folder called data set, where we are going to be using these data sets to do our calculation. Okay, all the experiments are going to be around that. And today we have 1, 2, 3, and 4. Okay, I'm right now on experiment 1. You can see. Okay, and I am now doing statistics refresher, where I'm saying whatever the data is, whatever data here is. So when you see this, you can't see. Basically, the whole idea is this: inferential. because this is where the whole game is. What do you infer? What do you understand from that data? To infer, you can't infer anything from this, right? You cannot infer it. Can you infer anything from this? Whatever you're seeing? No, nothing can be inferred from here, right? This brings me to introduce you to statistics in the way in which has to be understood. How many, now you see the number of data points here? Now pay attention. The next 10 minutes is a decider. Okay, next 10 minutes, what I'm going to tell you is something which is it's going to make everything clear to you. 20,641 data points. The first variable here is about longitude, latitude. Okay, this one is what? House, median. Okay, age of the house, rooms, bedrooms, population in that housing, right? The whole community. So if I want to understand this data, I want to completely, guys, in, hope everybody is in. Give me a thumbs up if everybody is attentive now, because this is the decisive moment, what I'm going to tell you. This is the takeaway of statistics. Okay, super. The thing is, I don't want to see all these things. I cannot go and study 20,000 data points at once. No ways. Is there a computation that I can do so that I don't have to see this at all? I don't want to see all these numbers. I want just a few computations. So then we discovered, let's take the average of it and put a mean value. So somewhere you get a mean value of, say, 45. Okay. Somewhere you get a mean value of 45. So now housing median age, or this is median age, of course. When you if you just take the mean value of this median age, that is fine. So this mean, the calculation of the mean was supposed to give us the confidence that the entire housing median age is distributed around this number, so that I can just close this and only look at this number. But we can't rely on this number. Why? Because what if in this entire 20,000 data set, all the houses are about 5 years and one house is around 200 years? Suppose you have 15 houses. Okay, I'll not take 15 houses. Suppose you have 5 houses. House is 2 years, another house is 3 years, one house is 4 years, one house is 5 years, another house is 50 years old. Now, if I want to block this off, and if I want to say what is the mean of it, how much it will be? 55, 59, 61, 64. 64 divided by 1, 2, 3, 4, 5. 5. Around 12. So now the mean age of this house is 12 years. But some is very new, right? Some is just 2, 3, 4. Because of this, the entire mean calculation got messed up. This is the outlier. Now, what we should do? We should have a new computation where I'm not going to get affected by the outliers. Because what is my end goal? I want to close all of this. I want a few numbers. But mean is not helping me now. So I'm going to go for median. What median does, you all know. We rearrange this. It's already rearranged. We rearrange it in ascending order. Take the mid value. That is a median. So the mean here is 12 years and the median is 4 years. Now you see the percentage difference between median and mean, 300%. This should tell me how the distribution of this. So that brings us to the very, very important terminology called distribution. So everything is a distribution. This whole thing is a distribution of housing mean. This whole column is a distribution of total rooms. This whole column is a distribution of total bedrooms, total population, total household. What is it? Distribution of these. And all these concepts that you're learning, mean, median, standard deviation, it is all there to make you understand how this distribution is with just a few numbers. With this one, you already understood. If you ask for the median, if you ask for the mean and ask for the median, just by comparing this, you are understanding the distribution. Means what? See, if mean is 12 and median is so less than that, then don't you feel that you already know that there is an outlier here? Otherwise, mean and mean, if everything was equally distributed, then median also should be around the mean only, right? See how two different concepts gives you clarity. After that, that was still not effective because there are many cases where the mean and the median could also be the same, because in the center it could be same, but later on, after going towards some value, you will see something very different. So the mean and the median is not able to completely conceptualize or hold the real nature of this distribution. It is not able to hold it. What we do then? We bring new computation. Mean, median is not enough. So what we do? Just take this example, okay? What we'll do, just take this example. And suppose the mean around this is, looking at this, I'm getting around 45. Okay, now interesting stuff. Give me a thumbs up if everyone is clearly understanding this, because this is going to be next level now. Okay, thank you. Now we bring in a new computation. We will compute not just the mean and median. Now we want a new vector which says how far away is this particular value from this mean? How far away is this particular value from this mean? How far away is this particular? So every time if we take the difference, so we are taking the difference from the mean. So we get some values, x1, x2, x3. All these are numbers. Now all this difference from the mean, x1, x2, x3, you square it, then you sum it, and you take the average of it. Okay, so the average of the squared distance from the mean. The average of the squared distance from what? From the mean. What is this? Can anyone tell me? Can anyone type in the Q&A what is this called in statistics? And then starts with V and ends with E. Next is A. This is C. Anyone who wants to type it in Q&A section, what this is? Variance. Okay. So this computer is called variance. So now we brought in a new concept. Mean was okay, median was fine, but then we wanted a new term called sigma squared. It's this whole symbol is for variance. And what is it saying? This variance is saying how is the distribution from its own center? The center, the mean. So the mean is very, very important. You see all the algorithms. See, one is you build the model, then the second one is you evaluate the model in machine learning. You build a model, then you evaluate a model. To evaluate the model, you need all the statistics concepts. How good your model is, you need all these statistics concepts. Like, hey, did your model cover all the variance in the data? So when somebody says like that, how do you intuitively understand what am I talking about? Now, this is what I'm talking about, the variance. Because I am computing from each data point, from its own center, how much is the difference? And I want to see the drama of the difference. I want one number to tell me how much is the variance. Everyone following? Thumbs up. Give me a thumbs up. I'm going to show you now a real value. A real interesting stuff. Great. Okay. So now, what is variance telling you? Variance is telling us how much is the distribution varying. When will you think that the variance will be 0? Suppose I have this data set 5. So, okay, suppose I ask all of you, how many hands do you have? Or I ask all of you, how many heads do you have? You all have one head. So you are going to answer 1, 1, 1, 1. All of you, 126 people. 126 people now. Okay. So 126 people, all of you are going to give me 1, 1, 1. What is the variance of this data set? Don't calculate. Just tell me, is there any variance in this data set? No, right? It has to be 0. So you want to prove that, you want to you want to compute this one, say 1, 1, 1, 1. What is the mean value of 1, 1, 1, 1? 1, 1, 1, 1 of 126, but add up 126 by 126 is 1. So mean is 1. 1 minus 1, 0. 0, 0, 0. Square it, do whatever you want, you'll get 0 only. Now you understand why variance is important. Now you see. Can I not completely cut this off just by seeing the mean, median, and variance? I don't need this column at all now. I just want the housing median age, housing median mean age, and the variance in the housing median age. Only with these 3 quantities, I can understand everything about this distribution. That's what. Now what? Now let's get back to that original definition of statistics. Original definition of statistics was that statistics is about how true your guess is, right? So you can take a guess now, right? You know the mean, you know the median, you know the variance. So if I play a game with you saying, now I have told you the mean, median, and variance. So if you guess, now I have, if I just rub this off, okay, and I'll show you this. I'll show you this this screen right now. You don't know which number is this. This one. I'll ask you, can you guess? Still 20,000 data points. You're not seeing it. I'm telling you. There are 20,000 data points. The 18th data point, I don't know. If you guess it right, I will give you 100 rupees. You need, if you want to really guess it right, you need the mean value, median value, and the variance. So if you understand the mean, median, and variance, you can take a calculated guess. At least your probability of being right increases. That's what statistics does for you, okay? It is only going to help you take better guesses. The same thing repeats for everything. Wherever you see a number, you can calculate the mean, median, variance, okay? Now, of course, what is missing? Standard deviation. Now, what is this standard deviation doing? Why this standard deviation is important? Okay, so standard deviation is square root of this variance, so you get this as standard deviation. Now you saw that distribution over here, right? So this mean this mean was 45, and let's just take this much, okay? This is okay. I'll take this. This looks like a good. This one, and I will make space. Let me make space, because this is even more important. This concept, what I'm going to tell you now, is actually very important. I hope you're all completely in the zone, in the flow, to make sense of it. It's okay, even if you are not, you can again watch the video. But here it goes. Is that okay? Here, let's just take. Just this is our data set, okay? Just think about this as, and the mean value is 5. So I'm going to make it even more interesting by putting different colors, the difference between this. So using the computation of the difference between this and squaring them, okay, you bring this all here, you square them, sum them, you will get some variance, sigma squared. You will get a variance. Now, then you square this, you take a square root of this variance and you will get a number. In this case, let's say 50, 52, 40, 42, 52. When I look at this, I have an intuition that you will eventually get a square root of the variance to be around 4 or something. Standard deviation around 4. Now, the difference between 50 and 45 is 5. Number 5. Okay. And the standard deviation is 4. I want to express this 5 in terms of 4. What will I do? So I will do 5 by 4. So 5 by 4 is 1.25 or something. Okay. You take that, then you do 1.25. Now, can I say that this 5 is equal to 1.25 into sigma? Everyone following? Thumbs up that if you followed, or you can say repeat. You put a 1 if you followed, type in a 1 if you followed it, type in a 2 if you did not follow it, because this is the most important thing. Until here, everyone, please use the Q&A to put 2, number 2. If I see a lot of number 2s, then I'll repeat this concept again. Nobody is going to type in number 2. So much. Nobody is using Q&A. Nobody wants to type in a word. Oh yeah. Oh, this never got refreshed. Okay. Oh, 2 people have this. Okay, I can see 2s. I can see 2. Okay, I can see a lot of 2s. Fine. I'll again explain it. No problem. See, what was the whole point? Okay. There are 126 people. I want to give you a disclaimer. There are 126 people. Not everybody is going to be on the same level of absorption. Okay, it happens in your class also. Not everybody. So I'm going to, I'm going to make sure that we spend good amount of time on foundation, so that those exercises, when I give them, should be cakewalk for you. Okay, I'm pretty sure, because we are all professors, we're all at a certain level already in maturity. If I tell you the gist, no, you will catch it. Okay, so that's why I'm going to make more effort getting you to see the problem the way a statistician sees it. Once you know the way in which you will see the problem, everything gets sorted on its own. Okay, so that's why I will repeat it. So please, people who have understood it, bear with me. Okay, let's go back again. You have this distribution, lot of numbers, 20,000 numbers. I can't understand it. I want certain measurements where just those measurements should give me everything. So what do? I first calculate the mean value of it. What mean tells me? Around the center, what is the common number? That's what the mean tells me. Fine. I say I get 45. But now, with this new number that you have got in your mind, and then I play a game. I play a game with you. And I say, hey, can you guess this number? You know that the mean is 45 now. Can you get this number? So if you guess this number as 45, you win. But this whole distribution could be 10, 10, 11, 12, 1, 15, blah, blah, blah. And this could be 200. Add this up, still you'll get 45, right? How then a guess is wrong? You're taking a big risk here. So which means what? You cannot take the decision of guessing just using the mean value, because mean value is affected by outliers. Some people have, login problem. Why? Acha, we'll send the video recording. Okay. People, okay, so I'm getting messages that some people are not able to log in. So I was answering my staff. All right. So getting back, it is affected by outlier. Somebody, some age, some house is 200 years old, and everyone is 10, 11. When you add it up, mean will get affected. No. So which means what? Mean alone is not enough. Median we want. So median is going to give us the difference between mean and median. Now will tell us whether this effect is there. So if the median turns out to be 12 and the mean turns out to be 45, And now I ask you to guess, will you guess 45 or will you guess 12? You will guess somewhere in between. Because what is your end goal? You want to be right. You want your guess to be right. The game today. That is prediction. Okay. So that's the whole takeaway. The whole game today is, are you able to take safe guesses? Is your guess very close to the truth? We don't know the truth, but we have the data, and using some techniques and skills, we want to take the best guess. To achieve this, all these computations are there. Next, we calculate this variance. Okay, variance, how did we calculate? By taking the difference between this. Between what? Let's say you take this small data set here, take the difference from 50 and 45, you get 5. 52 and 45, you get 7. 40 and 45, you get 5. 42 and 45, you get 3. 52 and 45, you get 7 again. Okay, you get 5, 7, 5, 3, 7. Square all of them. You get 25, 49, 25, 9, and 49. Add them all. Okay, summation. Take the average of this. Now that value is the variance. So that is why it is called average of the square distance from the mean of each point. Think like a, don't make it very complicated in your mind. Think like you are really experiencing somebody discovering this for the first time 100 years ago. Think you are in that situation now. 100 years ago, you are observing a data or some mathematician discovering a new system of understanding the variance in a system. Now, variance became some value. Go look at it. If all the houses are 4 years old, is there variance in this? Because what is the mean value? 4. What is the difference between 0, 0, 0? So you take a square distance average of it, you get 0. Variance is also a number. Mean is also a number. Median is also a number. Mean is also a number. When you have all of this, you get this computation. Now, what I was trying to tell you is, when you take the square root of it, you get a new number, and we call that as standard deviation. Now, standard deviation is the currency of change. See, currency means, in India, currency is rupees. Every transaction happens in rupees, correct? You go to US, it's dollars. In statistics, it is standard deviation. I'll explain to you now how beautiful it is. What we were doing, we were trying to find the distance of this number from its mean. That's it. The distribution is this much only now. Only of this much. The mean of this is 45. The difference from each number to the mean is 5. We have calculated that the standard deviation is 1.25. The standard deviation is 4. I'm sorry, not 1.25. The standard deviation is 4. The distance is 5. And I'm saying phi is equal to 1.25 standard deviations away from the mean. Can you do it same for 7 now? How many standard deviations is 7 away from the mean? How many standard deviation is 52 away from the mean? 7, right? So can you express 7 in terms of standard deviation now? For that, you have to do 7 by, so 4 ones are 4, so 1, get 3, 7s are 0.78, so 1.72. Okay, see, the 7 now becomes 1.72 sigma. 5 is 0 sigma. 5 by 5, 1, 1. 3 is again 0.75. 7 is again 1.72. So you are expressing everything in a new context. For how many sigmas are they away? Here, now I'm going to tell you very, very interesting stuff. Because This interesting stuff, unless you understand the previous concept, you won't understand the next concept. Okay. So tell me, give me a thumbs up if everybody is on board. If everybody is on board with this. The people who have given two, I hope, you know, you can watch the video again, but fine. Now the interesting stuff. For this, I'm going to have to use. Anyway, I'll just remove this. I'm going to go to the. I'll just use this. Now you see, you must have seen this many times. This whole thing, this distribution. Okay, so you have all this 1 sigma, 2 sigma, 3 sigma, -1 sigma, -2 sigma, -3 sigma, and we got all this data over there, right? We had the mean value. We had the first one was 1.25 sigma, second one was 1.71 sigma, third one was 1 sigma, fourth one was I think 0.3 sigma, the fifth one again was 1.75 sigma. These are all 1.25, 1.75, 1 sigma, 0.3 sigma, and all that. Right? This distribution, how many data points in this fall between 0 and first sigma? So if there are 10,000 data points here, we can have all these numbers, all. And we can now say, around in the 10,000 data sets, 500 of them are between sigma and sigma. So this 1.25, 1.71, 1.71 is where? Between first sigma and 2 sigma, right? Because this is more than 1 sigma. So 1.25 and 1.75 here only. And if we come to know that in the data set, thousands of data is here and 5,000 data is here, another 1,000 is here, another 300 is here, another, see, you understanding this? That is why it is called the probability density function. Because you are just mapping all the sigmas over here. What is the sigma denoting? Sigma is denoting the deviation of each data point from its. Who will complete this? Can anyone type in? From its deviation from its. I'd like to have seen this. Okay. So, I mean, of course, we wanted to do ML lab and all that, fine. But eventually we'll cover all the experiments. Don't worry. Now everything will make sense. Okay. But you should see in data science and machine learning, if you are going to go advanced into that, everywhere you will see mean and standard deviation. Everywhere. But I hope you're appreciating now. Why mean and standard deviation is important? Because mean gives you the reference. Right? If you don't have a measurement system, no reference, no measurement, no prediction. So to measure a distribution, you always wanted a reference system. And the mean of the distribution itself is a reference, always. What else can you do? I mean, if you really think about it, can you simply create some information out of anywhere? We can't, right? We have to use up whatever is there in this. What was there is a beautiful number called the mean. Mean is usually not enough, so you get the median. Then median and mean both are not enough, so you find something, a new thing called variance, and you understood what variance is. And the square root of it is standard deviation. And now comes the awesome thing, which I want to tell you. How many of you have heard of something called 6 Sigma certification? 6 Sigma certification. 6 Sigma certification. The 6 Sigma certificates are given to people. People actually get 6 Sigma certification. Means what? Means if a person has a green belt or some blue belt or some other belt in 6 Sigma, you know what that person is capable of? This person is capable of building a manufacturing process where the probability of finding a faulty device is in 6th sigma. The first sigma is 66% of the data point. The second sigma is around 13%. The third sigma goes to 6%. Fourth sigma goes to 2.1%. Fifth sigma, sixth sigma is what? 0.01%. So you are actually 0.001%. So you are actually doing 1 by 1 million. Means if this person is hired by Colgate manufacturer, he is ready to build a system where every batch of 1 million Colgate paste that comes out, only one faulty Colgate sachet is there. Only one. Because that's the level at which process, the definition of the process that this person can build. That's why it's called Six Sigma certification. So sixth sigma is actually coming from your PDF only. And that sigma is nothing but the sigma that you studied just now. Okay, so all these are connected. So I just wanted to make, because some concepts are best explained when it is ripe in your mind, so that the connections are made in your brain, and then you start appreciating the practical value of what you're learning, right? And of course, the same thing can be imparted back to your students. So that will be nice. So, is there a break time now? Okay. Oh, scratchy? Why is it scratchy? Okay, voice is scratchy. Is everyone experiencing my voice scratchy? I'm going to get something different this time. Not audible. Okay. This. Hello. What now? Audible? Better or? It's better now? Audible, it's audible clearly, audible, your voice is getting stuck. Okay. I think from my end, it's a 5G connection. Some people are getting it through. So if somebody's the voice is getting stuck, it could also be because the bandwidth that you are experiencing on your end, because these are all high dense voice. Maybe it's because of that. So don't worry about it. Let's just adjust with that, and we'll give you the right video. Video is getting recorded anyways. So that will be made available to you. Don't worry about it. I'll even give you all which concept is. I'll break it down the video, right? In which concept is where. We'll do it from our team end so that you get the video. Don't worry about it. But moving on. So that's what this whole distribution is all about. So let's just go and now come here. Now this will start making sense again. Descriptive, inferential. In descriptive, you ask these questions. Where are the points relative to each other? Are the points relative to each other? You want to ask this question about the data set. Think about this question. I'm not going to, this is a very different approach to statistics, okay? Are the points relative to each other? Is this question important for you? Do you want to know this? Moving on, next question. What are the most common points occurring in the distribution? Always you think like this. See, where are the points relative to each other in the distribution? What are the most common points in the distribution? How often do the data points occur in the distribution? What does the spread of the scores look like about the distribution? The whole thing here, you see this, the whole thing here till here is descriptive. Okay. Now, when it comes to inferential, if you are able to understand all this, using this, you can now do this. How do I prove the theory I have about my data's behavior? Because you see, when you go here and you see the graph, carefully observe this, huh? When you look at the graph like this, you see that the population and frequency of population, these are household data. So mostly you have communities where people from 0 to 5,000 people in a community are existing. Okay. So generally you have 0 to, if this is 5,000, and I'm guessing this is 0, 1,000, 2,000, 3,000, 0, 500, 1,000, 1,500, 2,000, 2,500, 3,000. So the difference here is 500 each. Okay. So around 2,000 members colony, 8,000 colonies are there where there are 2,000 people staying. Like there are 8,000 colonies. Each colony has 2,000 people, the housing, the household, that societies are there, right there. That's what the inference is. When you see this, you now say that, okay, in California, usually you will, that's the inference, right? In this housing data, you say in California, I think mostly housing colonies have about 2,000 people. That's what you feel like saying, right? That's what the graph is saying. So if you infer that from that, somebody should tell you whether you're right or wrong, correct? If you simply infer, my hypothesis is that around 2,000, there are a lot of, mostly all communities on an average has 2,000 people in it. That's your inference. That's your takeaway now. But who will tell you whether you're right or wrong? Data will tell you. Using what? These computations. Next, if a new colony is discovered by somebody, will you still predict that that colony will also have 2,000 people? That is this prediction. Okay. Generally, all of statistical inference, statistical learning is around this one. Now going to the next. Where are the points related to each other is called position. What are the most common points? It's called central tendency. How often do the data points occur? Frequency. See, that was frequency. What you just saw. You see? Frequency. Okay. Now, what does the spread of the score look like? You have just studied that. Spread of the scores. Spread means variance. That. How do I prove the theory I have about my data's behavior? It's called hypothesis testing. There is one algorithm here, which is your find S algorithm, to output a description of the set of all hypotheses consistent with the training example. See, I'm not simply giving you the fundamentals for no reason. You will see these stuff coming up again and again. There is no point that when I come here, I explain that it doesn't make sense, right? So I'm putting all the foundation before, and when I come there again, I'll explain. That way there will be reinforcement of that, right? So this hypothesis testing and then estimation. Once you know that your hypothesis is right, then you build an estimation on about the hypothesis. To do all of this, we have, now we come to the final. Position are quartiles and percentile ranks. The central tendencies are called mean, median, and mode. The frequency are called counts and percents. The variations are called, for the variation computation is variation, standard deviation, and range. And hypothesis testing, you have Z-test, T-test. For estimation, you have parametric estimation and confidence intervals. Usually what happens is in school, we are taught this level first. And I myself also went through the same schooling system. And for me, for a lot of time, I was like, why am I calculating mean, median, mode, what? Why am I doing all these things? Somebody tell me. But trust me, if somebody had told me all this, I wouldn't be able to understand it. Now we are at a different level, so we came top down. I hope you appreciate the approach of the top down, because this way we are all mature. We understand the questions, the veracity of the questions, and then we go towards the computation that makes sense. We just studied mean, median, mode, variance, and what are we going to do with this? Central tendency, mean, median, and mode gives you the central tendency of the distribution. Means what is the tendency of this distribution around its center? That is what are the most common points, and that helps you describe. That's how you should see it. All this helps you describe. All this helps you describe the data set. All this helps you describe the data set. Even this helps you describe the data set. But this Z-test and T-test and hypothesis helps you to make inferences. This parameters, and this we will not, this is not in your lab at all. So maybe in some other lab where it is covered or some other subject it is covered for you in your syllabus. So this we are not going to talk about. We just need this information. Okay. So I hope these things are a little clear. Fine. Everybody is fine with this. Close this and we come back to our data set. And all you have to do is go open Jupyter Notebook the way I did